This video is sponsored by PCB-based. Welcome everyone. In this video I'm going to finish this project with the front panel and the ADS1256 module. So I finally got the proper pre-crimped cables, these guys here. So now I have the chance to finish this thing properly. Previously I attempted to crimp the cables manually, but as you can see these are very tiny connectors, so this and my crimping skill did not really made it possible. And then in the previous demonstration I showed you some examples by directly soldering the wire to the PCB. So if you look at the back panel here, then I had the connectors here and here. I will show it on the real project, and then I just directly soldered things on these tabs instead of plugging it in because I could not make the cables. And then those wires were then connected to these bottom connectors here, and then they are on this PCB, as you can see, connected to the corresponding pins up here, and these are the GPIO pin numbers on both sides. So then now, with the help of these pre-made wires, pre-crimped wires, I can just measure the correct lengths that I need. Then I will cut the wire where I need it to be cut, and then this side goes in the corresponding connector, and then the other side will be obviously soldered to the corresponding hole down here. So let's just quickly open this thing up. This is the most recent PCB with the front panel things, and let's see what I need to fix here. So here we have the soldered connections, and this is how it looks like on the rear panel here. So I will ditch this panel, desolder these wires, and then I have the corresponding connectors. Just to repeat what they are JSH SH 1.0, so 1mm pitch JST connector, and then one is 15 pin and the other is 13 pin. So in total we have 28 pins, which are mostly GPIO pins, but we have a few like power pins like 5 volt, GND and 3.3 volts as well. So that will be our task in this project. And then of course, when I finish all of this, there will be some demonstration, and how I will demonstrate the circuit, and I will demonstrate how it works. I take this small I2C LCD, and then I will just print the readings of the ADS1256 on this panel. Probably I will make 4 lines for the 4 differential channels, and we will see how it works. And if you are interested in this PCB or in this project overall, please visit PCB-based website, especially my project page. Link is in the description. So if you visit my project page on PCB-based website, you can find my project there, and then the project includes both the PCB, which contains the ADS1256 and the RP2040 circuit, and the front panel and the rear panel PCBs, so you can make it as a whole project. And if you don't want to assemble this yourself, you can ask PCB-based, and they have a great assembly service where they can provide you all the parts and you will receive a finished complete product. So now all we have to do is I will need to remove these cables, and then I will also have to measure the cables which will go into these 2 connectors together, obviously with the corresponding connector. But first I will assemble the wires for the connector, and then I desolder this, because then after that I can solder the wires here immediately, basically. So let's do that. panel is done. It's soldered properly, so let's put everything back in the enclosure. So here we still have the rear panel, which will match this part. And it slides in properly. And then, as you can see, this is what I was talking about in the previous video. There is sufficient gap there, so I can tuck in the cables, hopefully neatly. And once they are tucked in, I can just close this off and seal it. So something like this. So now it's completed. So now I quickly go to the computer and program it so it can drive the display, and then I will come back and show you how it works. So I have returned with the device. I just put it on this OmniFixo fixture just to hold the screen properly. So then we have the connections there. I'm using the secondary I2C connections for this particular display because the primary, which is pin 6 and pin 7 in the GPIO pins of this microcontroller, pin 6 is occupied by the SPI, which is driving or communicating with the ADS1256 chip. So instead of using that I2C port, I'm using pin 26, 27, but I will explain it in more details when I actually show you the code. And then let's talk about this. This is just a test circuit. It's a 10K potentiometer and then 4 additional 10K resistors. So it splits the voltage at each outputs. So starting from the yellow down to the orange, we have 4 outputs. And then how I will connect this, I will just demonstrate it on this panel. So as I have explained a million times, the module supports 2 modes. One is the single-ended mode, and that's where we have 8 channels, so A0 to A7. Each of these terminals are a positive terminal, as it is indicated here, and then these are all ground terminals. So then A0 plus 1, whichever, because it's a common connection, common terminal, that is one channel. A1 plus one of these is another channel, and so on and so on. But that limits the measurable voltage between plus 5 volt and 0 if the buffer is not used. And then there is a differential input when we only use the positive terminals, but obviously then we have only half of the available terminals here, because one has to be used as the plus and the other has to be used as the minus terminal. And actually, programming wise, the ADS1256 can pair up whichever 2 ports you want to use. So you can have, let's say, the A2 as the positive input and A7 as the negative input, because you can define the multiplexer that way. The multiplexer doesn't care which 2 channels have to be connected, but in my case, to keep everything consistent and more logical, I combine the adjacent channels. So A0, A1 is channel 1, and then A2, A3, channel 2, A4, A5, channel 3, A6, A7, channel 4. So then I will have 4 channels, and that's how I will connect this up. So A0 will be the first positive, A2 will be the second positive, and so on up until the orange wire. And then I will just connect A1, A3, A5, and A7 to the ground, because that will be common. We don't measure, let's say, positive and negative voltages, only positive. And then I will use this multimeter just to compare the readings with the multimeter and with the display here. Let's set the things up. I will wire this up, and then I will explain you in more details what is happening. So here is the setup. Here at the bottom you can see that we are already printing some information. They are the 4 channels. Top is the first channel and the bottom is the last channel. And similarly to that, then from left to right we have the first yellow, second green, third blue, and fourth orange outputs from the voltage divider. And now actually I should turn this to the other direction. So now this 10K potentiometer is maxed out. So now what we have here is then these are the voltages according to left to right outputs. So everything is wired up as I explained earlier, and also there is an extra wire which goes to the ground, because otherwise the ground is not referenced to the power supply properly. So then the voltages which I read with the multimeter and the voltages which I read with the screen might differ due to the different grounds. And then yeah, power supply comes in here. So I just turn on the multimeter and check the voltages. So yeah, we can go backwards. So try not to block the display. So the last channel here is 8833, so it's close enough. And then the second last channel is 175.27, again close enough. And then here we have 2.634, again close enough. And then the first channel is right here, 3.511, and again it's close enough. Whichever is true, I don't really know. I haven't calibrated any of these units or devices, so we just say that we are satisfied with the values we see. Now I can change this, so I don't have equal resistors through the resistor ladder, and you can see that the voltage is changed. So I just randomly poke somewhere, let's say to the second channel, and that is 2112. And yeah, we have the same on the display. And then this should be 1.4. So there it goes. 1.4044 versus 4061. So actually what you see here is then 2 millivolts difference, because this is 1 volt and then 100 tenths and the millivolt difference. So that's quite okay. And then here 7087 and 708 something. So this is now like 100 microvolts difference, or it's in the order of magnitude of hundreds of microvolts. And I'm not using any fancy PGA setting and anything. So actually the amplifier in the ADS1256 is set to the largest value. So actually these numbers could be improved, so maybe they could be even closer to each other. But as I said, they are not really calibrated, so we don't know which one is true or which one is more true. So let's just say that my ADS1256 can measure as good as this multimeter right here. So that's for me is enough. And since I did a slight modification to the example code, which comes with my library, which belongs to the ADS1256 project, I want to show you the code. There are no modifications done to the library at all, or to the ADS1256. I just want to show you the code which basically drives the display. So if you want to replicate this experiment, you can have an idea about how to deal with this display and how to deal with the library. So let's go to my computer and I show you the things related to the display and the code. Okay, so we are looking at the example code which I provide for my ADS1256 library. So I will just show you the modifications that I did to the example code, but I will not go through the code obviously because I showed it multiple times and it's available on my GitHub. So what we have here is that I'm using this U8G2lib library, which is a very good universal library for displays, OLED, LCD, you name it, it can probably drive the display. And then since I use I2C, I include the wire library as well. And it's not really important because this is just related specifically for my specific PCB, but still, if you buy my PCB and work with it, this can help you. That for my specific PCB, this is how you have to define the constructor for the ADS1256 library. So that's that. And then these are all the same. However, here I just added the I2C1 because the default is the I2C0. So the one SDA pin is located at the GPIO 26 and the SCL is located at the GPIO 27. So that's we have to use. And then I use this specific line to create an instance of the library which drives the display. And here I only put in the rotation. I don't add the SCL and SDA pins and other things that you can find in the library because this is how I figured it out that it could work. So then there's nothing extra here except starting from here. So we are using the alternative wire or I2C, which is the wire 1. So then first I have to set the SDA and SCL pins. So this is how I did it. These are already defined. So SDA1 is 26, SCL1 is 27. Those are the pin numbers. And then after defining these pins, I just start the I2C port. So then we have the display part. Before actually making the code, I ran an I2C scanner with this code. And then what I did is that I found the address of the display. And then this is how the library requires us to give the address. So actually you have to multiply the address by 2. Don't ask me why, but it is written in the library's documentation. So just read it, this specific library's documentation. And then yeah, I initiate the screen, clear the buffer, set the contrast to 140. This was also a bit cumbersome because in my previous examples where I used this display in other projects, the contrast value was totally different, so I could not see anything on the display. But then I played around with this value and I found it to be sufficient with this 140 as the value of the contrast. And then what we have here is that I just selected some random font. You could see some modern looking, digital looking font. So that's what we have. And then the font mode here is basically just how the fonts are printed and how they are printed on top of each other. So let's say you printed a line and then you want to refresh the display. Then how will you print the line in the next, let's say, frame? And then instead of printing over the already existing text in a way that you just literally print over it, so you would see the previous characters, then this font mode actually replaces the numbers and then it prints over a blank area. So that's how it works. And then I just chugged in this part. You can see this separator line. Below that, this is my typical code that I have already explained many times. But then here, I just put everything in an infinite while loop. So then only the currently selected code will run. So what we have here in the loop is I just created a character array, str, holds 10 bits. So 10 or more specifically just 8 like usable characters, because we have to account for the ending character in this string, and then also the negative sign if there is any. They are not really number characters, but yeah, whatever. It's not important. And then I also have the float acquisition value. So it's a float variable which is called acquisition, and I just store the number in that in this variable. So then what we do in this, so actually now the selected part is our loop. The code will not go down and take care of these things. It will only stay in this. Nothing else, because this is what I need for the demonstration. So what happens here is that I cleared the previous display, and then we have to iterate through the 4 channels that we have, the 4 differential channels. So then what we have here is that actually we go from inwards, or we go from the inside and we go outwards. So first of all, we do this cycle differential. So this will read the first pair of pins on the ADS1256 input, and then it will return with a digital value. It will be just some number between 0 and 2 to the 23rd power minus 1. So that will be it. But that has to be converted into voltage. So then I wrote a function which then takes this output and converts it into voltage in volts unit. And then that is passed to this variable. So then that variable is then passed to this D2strf function. I showed it in several of my codes where I have to deal with floats and character arrays. So what happens here is that we take the float number, and then we tell the code that the printed number, so the conversion of this float, will be stored on maximum 8 digits. And then the maximum number of decimal digits, so on the right side of the decimal dot, so the 0 point something something, that can be maximum 4, and that you could see on the display as well. So these are the parameters. And then this acquisition variable, or the content of it, with these let's say specifications, will be converted and put into the str character array. And then all we do is that we call this draw str function from the library, and then I push in the characters 3 pixels from the left side. And then here what you can see is that based on the iteration in which step we are standing at, we print into a corresponding line. So actually in the first iteration, where j is 0, then this becomes 1. So we multiply it by 14, so that becomes 14. Then x3, y14 character coordinates on the display. That will be the starting position for printing the text, and then we print the contents of the str on the display. And in the next iteration this becomes 1, so this will be 2. 2 times 14 is 28. So then the next channel's value will be in the line which starts at the 28 pixel position, and then the next one will be 42, and then 56 or something like that. And then that's how we print the 4 numbers under each other, as you could see it on the in the demonstration. And as you can see, I have a few commented lines. I just wanted to check it on the serial port as well, but it's not necessary because we have it on the display. But yeah, that was that. But then when we sent this drawing, after we finished the for loop, we basically put 4 numbers in the buffer, but it's not on the display yet. So then this send buffer code will take care of the actual printing on display. So that's that. And then yeah, I just put a delay here. It's actually unnecessary if I set the sampling frequency properly, but I did not care about it too much, so I just put a delay there. And then that's all basically. So this code runs over and over, and it writes the parameters on the display that you could see. And with this, I'm finished with the demonstration basically. So if you want this code, and more importantly maybe, please visit my Patreon site. I put this code there, the INO file, so you can just download it and use it. Or yeah, if you don't want to support me, then you can just copy it from the display and type it in yourself. And also, if you are interested in the PCB, please visit my PCB-Way project site. I have everything there, and you can use PCB-Way's assembly services if you are not that experienced with SMD soldering and so on. And then you can get the turnkey solution. And then you can just go to my GitHub, you can download my library, and you get this whole file with the library for free, so you don't even need to support me if you don't want. But what is more important is that you can download it and then just upload it directly, and it works. And also don't forget to visit my website. I put some information there, which might not have been shown in the video. There could be some more information for you and some pictures and so on and so on. So I hope you liked this video. I hope you learned something, and see you in the next video.